This is me going over lab 2. So part 1, you're going to start by clicking the link, which will take you to this. You're just going to save it as a text file. Then you're going to click this link right here. And then you will test. Then you're going to start your Wireshark, upload the file. Then you're going to stop it. Now we gather this now. I'll go to the questions. So starting it off, what is the IP and TCP port number used by your client computer source to transfer the file from GaiaCS UMass edu? So you can see here, this would be our IP address using port. The source port is 1161. For question 2, what's the IP address of Gaia? That's going to be 128.119.246.12 with a source port of 80. So that's where TCP sent. Go down here. The sequence number right here is 0. The flag is set to 1, so it's set. Now for 2, the SYN ACK right here. You can see that the sequence number by SYN ACK is 0. But the value of the acknowledge field is 1, and the value of SYN is 1. And together, that means it indicates that the segment is a SYN-ACK segment. 3 was a segment number of a TCP segment. So host HTTP post should be, there it is. HTTP post right here. The segment is posting right here. It should be 1. And regarding question 4, consider the TCP segment containing the HTTP post in the first segment of the TCP connection. What are the 3 okay. What are the 3 segment numbers in the first 6 segments of the TCP connection? It's going to start over here. So you have put the flags away. Here's 1, 2, 3, 4, 5, and 6. These are segment numbers, and the acknowledgement numbers are 6, 9, 12, 14, 15, and 16. Now the time sent between those would be right here. 4, 5, 7, 8, 10, 11. As well as the acknowledgement times of 6, 9, 14, 15, up 12, and 16. And to get the RTT, you're going to want to subtract the time sent from the ACK time. Then to get the estimated RTT. That's the formula right there. The first one you're going to start with is the RTT of the first of segment 4. And you're going to input that into the estimated RTT in the equation. And you're going to use the sample RTT of the segment you're trying to find for segment 5. It would be 0.875 plus the estimated segment of segment 4 times the estimated segment of times the estimate RTT of segment 4, excuse me, plus 0.125 times the RTT of the sample RTT of segment 5, and that would give you 0.02845. And if you keep doing it, you're gonna find the estimated RTT of each value of each segment. Now for number 5, what is the length of each of the first 6 TCP segments? So the first segment have the length of 565. And the rest of them, like 4, it's gonna have 1460. So if I go to 7, 1460. If I go to 8, 1460. And as for 10 and 11, 1460. What is the minimum amount of available buffer space advertised at the sender for each of the trace? What's the minimum? So if we check right here, let me check here from the first one. You see the minimum available buffer space is 8480. You're gonna see that right there. You go. And there's a lack of receiver buffer space ever thought of the sender. No, the sender is not thought of from the lack of buffer, as you can see from over here. Now onto the 7. Are there any retransmitted segments in the trace file? What did you check for in order to answer this question? There are no retransmitted section or segments in the trace file. By checking the time sequence graph in the trace, all the segment numbers from the source to destination are increasing over time, and since there's no segment number smaller than the segments near it, there are no retransmitted segments. So if we were to check statistics, get Stevens time sequence graph, you can see that none of the sequence numbers are smaller than the sequence numbers. They're increasing over time. Oh, put that away for now. Number 8. How much data does the receiver typically acknowledge in an ACK? Can you identify where the receiver in ACK is receiving each ACKing at every other received segment? Okay, so ACK 1. You said it was 6. Wait, check 9. There it is, 566. 5. We'll see as for each sequence number. There you go. 4. 566. It's acknowledged. 556. This one's gonna be 1416. That's what it's knowledge for. 1416. Right after. That's what it's knowledge. 556. Now for the next one. This is gonna be sequence number is 2026. And then the segment and then the acknowledged data is 1460. That's gonna be like that for 3486, 1460, 49, 46, 1460. This is 6406, 1460, 7866, 1140, 1147. That's the only different one besides the first acknowledged one. The rest of them from 8 to 12 are the same. Now for calculating the throughput for the TCP connection. Oh, what is the throughput? The bytes transferred per unit time for the TCP connection. So the throughput of a TCP connection depends on the average time period for the section. It is the ratio between the total amount of data and the total amount of transmission time. For example, if the first TCP segment has 1 byte, and the last it's 1 byte, and the last has 1,600, 164,091. Then when you subtract it, you'll end up with 1,600, 164,090 bytes. Transmission time of the first one would be 0.06477. And when you go down here, you'll see 5.4294. Then if you were to divide the total amount of data by the transmission time, you'll get 164,090 divided by 5.4294, which equals 30,222.492 bytes per second, or 30.22 kilobytes per second. That's how you calculate that value. And for the TCP congestion control in action, we're going to use the time sequence graph that we have to view the sequence number versus the time plot segments being sent from the client to the guide.umass.edu server. Can you identify where TCP slows start a phrase, begins and ends, and where congestion avoidance takes over? Yes. You can see how everything's like that. But when you zoom in, so start phase is from 0 all the way up to about right here. And I want to say that's more, that's 10. That's about 0.15 seconds. And from there, congestion takes place after that. And the data measured is a fraction of the window size instead of 1/3 to 1/2 of the window size. And that's part 1.